All right, this is a walkthrough of the practice test for test 5. This test is going to work a little differently than the others because it's just derivations. It's going to have 5 questions, 20 points each. Each one it asks you to do a derivation. The new material that's being covered for this mostly has to do with derivations using derived theorems. There will also be some derivations from no premises. And all of that is covered in the last homework exercise and reading. And we'll see how that works as we go through the practice test as well. The first 2 questions are just derivations like the ones you would have seen on earlier tests, like test 4. Because, in fact, they will be like test 4 because they will involve subderivations, and they'll be about that level of difficulty, although they will be drawn from a different pool of questions. So let's just take a look at this to start with. The first one on the practice test asks you to derive P implies Q from some premises. So, or want. We say want in this class. And actually it's just 2 premises. So, we can say 1, Q implies, or not Q implies C, and 2, not Q implies A and not C. And what we want is P implies Q. How did I learn to get rid of this, to not screw up the spacing? All right, we're just going to have to deal with this spacing as it is. In any case, our want line is P implies Q. And we know we can't do anything with the premises on their own. So we're going to want to use conditional proof because we're trying to prove a conditional. That seems easy enough. Why is it doing that? I'd go like that. There it is. So shift enter is what makes things less, gets rid of the extra space. Okay, so in any case, 3, we're going, and we want our horizontal line here. So, well, there's our Fitch bar, and 3, and now we're 2 levels in. So in any case, we're going to want to assume P, and then we're going to show Q, want Q. And this is for conditional derivation. All right, but P doesn't do us any good with these premises either. P doesn't even appear in them. So what are we going to do now? Well, the rule is that when all else fails, use indirect proof. So we launch a second subproof. And, and this line here has its own Fitch bar. I did that wrong. We want a single Fitch bar up there. We want a single line there for that Fitch bar, and then 2 for this one. Okay, and then on this level we do 3. 1, 2, 3, and we're going to assume not Q, because that is the opposite of what we're trying to prove. So this is for indirect derivation. And we're going to want a contradiction. No, we don't want a number here. This is the Fitch-Bar line. Now we can do 5. And now we can work with our premises, right? Because not Q was the antecedent to the two conditionals up here. And it's kind of a pain in the neck that this window is so small, but that's what we have to work with. So right away we see that not Q is going to give us C, and it's going to give us A and not C. Let's just do those two lines at once. This will be lines 5 and 6. Oops, 6. So this gives us, what was the contradiction? It's going to be C and not C. So C and A and not C. And this is conditional elimination lines 1 and 4. Yep, and then lines 2 and 4. Well, now we're almost done. Oh, actually, let's shorten this up. So what I'm going to do, actually, is I'm going to do, this will make it more compact and nice looking. So we're going to do A and not C first, and then for the next line, we're going to do, so this is 6 now, 3, check the numbering, 3, 4, 5, 6. We've got C there. And then for line 7, we do and elimination on line 5 to get not C, right? Now we've got the contradiction on the last two lines of the subproof, right? So it's C and not C. And that way we don't have to use repetition at any point. And so that is, and elimination on line 5. So that makes the proof more compact. Often I see people when they are starting to learn to do derivations, they use repetition too often. There's really only one situation in our system where we need repetition, and that's to move something to the end of a subproof via indirect derivation, because the last two lines of the subproof have to be the contradictory lines. All right, so there's our contradiction. The contradiction means we can pop out a level, 1, 2, we're out one level, and we can, we started out with not Q, so we can then give ourselves Q, negation elimination on lines 4 through 7. And Q is, of course, what we wanted in our conditional derivation. So now we go out to the next line, and we've got P implies Q. And that is conditional introduction on lines, 3 through 9? 3 through 9. 3 through 8. And that's it. That's it for that one. So that one was straightforward. That could have been a problem on the first test, or rather the previous test, but it wasn't. It's not that hard. The second problem is going to be drawn from that same kind of pool of questions where they're going to be like what was on the previous test. In this case, though, we've got a biconditional. We're showing an equivalence, right? So we need to do two proofs in here. One from going from the left to the right and one going from the right to the left. As a general rule, these aren't that tricky because the second proof is just a mirror image of the first. Let's see if that works for this one. So we're going to start going this direction, and then our premise is not P implies Q, and our want line is not Q implies P. Actually, I'm looking at this and I realize that if you use the derived rules that you can use later on, this proof would be shorter. And I'll accept that, but I'm not going to do that here. I'm going to do it without the derived rules. That way we can talk about the derived rules in the next section. So we're trying to show a conditional, so that means, as usual, we're going to use conditional proof. So we go here. There's our Fitch bar. And we start out with not Q, right? And our new want line is P. And this is for conditional derivation. Well, we still don't have anything, so this proof is actually going to work exactly like the last one. It's an indirect proof embedded inside a conditional proof, and that's a very common pattern to encounter. So we need another Fitch bar. And then for line 3, we're going to launch another subderivation. And what are we going to assume? We're going to assume not P. Why? Because that is the opposite of what we're trying to prove. So this is for indirect proof. And we're going to want a contradiction. And now we're rolling, right? Because not P works with our premises. For not P gives us Q. And that is conditional elimination on lines 1 and 3. And then 5, we just want to repeat line 2. And this is what I was talking about before with the rule of repetition. Really, the only time you need to use it is to get something to the end of a conditional of an indirect derivation so that you've got the contradiction in the end, in the last 2 lines, which is how the format of the rule wants it. So this is just R2. And now we're done. So we can just start popping out. We have our contradiction. So we pop out one level, and we started with, oh, I forgot to put this in here. Hang on. Oops. So we started with not P, and so now we have P here. negation, elimination, 3 through 5. And then for line 7, we pop out another level again, and we get our conditional, which was not P. Not Q implies P. Whew, well, we got through that. Unfortunately, we've got to do the whole thing again because it is it's an equivalence. We're showing that these two things are equivalent. Fortunately, since we figured it out going the one way, we can just do the exact same thing for going the other direction, right? So here we start by, in fact, you know what I'm going to do? I'm just going to cut and paste. Because all you have to do for this is reverse your P's and your Q's, right? So now we're going from up here, not Q implies P, Q implies P, to this side, not P implies Q. So on the next line, rather than assuming not Q, we're going to assume not P, because that's the new antecedent of the conditional. Our want line is Q. And then for the indirect derivation, we're going to have not Q. And then we get P from lines 1, which is not Q implies P, and line 3, which is not Q. And then we can get not P here. And again, we're still repeating 2. It's just that the roles have switched around. That gives us Q. I'm sorry. Is that right? Well, yeah, we're looking for Q. We're looking for Q now. And then we go down here and we say not P implies Q. So that proof was really perfectly symmetrical. And so that saved us some typing. Sometimes the reverse direction will not be that easy. Sometimes you will have to write up a whole new proof or use different principles. But in this case, it happened to be pretty straightforward. Completely straightforward, in fact. And there are not many problems in the problem set where in the question bank where you have to prove two statements equivalent. And when you do, it's generally two short proofs rather, so it doesn't turn out to be much more of a pain than the other proofs in that unit. All right. Problem 3 on this section is going to be pulled from a slightly different pool. And what's going to make it different is that sometimes there'll be some additional tricks. And this problem here is an example of that. So here, let's just set this up. This is a trick that you've seen in the homework problems sometimes, but you may not have remembered it and realized that it's a thing that can come up again. So our premises are not B implies C implies A. B or not D. C or D, and then we want A. Oops. Well, how are we going to get A? A does appear in the... Now, so this is the thing. Right now, you're thinking, I'm going to assume not A. And you're thinking this because you can't do anything with the premises, and you're not trying to show a conditional. So all that's left is indirect proof. And you could actually do this by assuming not A, but that turns out to be long and complicated, especially if you don't use derived rules. Well, here's another way you can use conditional proof. Sometimes you want to look at the want line, but other times the thing you want won't be right in the want line. It will be one step away. So if we want A, we know that A is here in the premises as the consequent of this conditional. What is the answer? So if we just had the other side of the conditional, if we just had not B implies C, then we'd be done. We'd get A. So that's lovely. But so really, not B implies C is a thing that we want. If we want it, then we can use conditional derivation to get it. So it winds up being just like a want line. We're still thinking about what we want when we launch subderivations. That's always important. But in this case, what we want isn't explicitly given in the want line. It's just it's going to be the step before what is in the want line. So sometimes you need to work forward and sometimes you need to work backwards. Right? So what we were doing there was we were working backwards from the conclusion. The A was what we wanted, and then we thought, how can we get the A? And we went one step back. So the way the subproof is going to go is it's going to be not B for conditional derivation, and it's want A. I'm sorry, want C. Well, now actually things should go pretty easy because not B works with the premises. Not B gives us not D over here, and then the not D is going to give us our C. So line 5, not D, D. And this is or elimination, lines 2 and 4. And then the next line, here I'm going to cut and paste because it's really similar. Line 6 is going to give us C. And that one's going to be or elimination on lines 3. Line 3 and 5. Right? Because line 3 is the disjunction, C or not D, and line 5 is one side of that disjunction, not D. So now we get to C, and we are, well, now we're done with the subproof, right? And so now on line 7, we can pop out a level, and what do we have? We've got not B implies C. And that's conditional introduction, lines 4 through 6. And in the past, and for almost every other proof we've done in the past, once we pop out of the last subproof, we're done. But that's not the case here because we didn't get our want line. We didn't get our want line in the subproof from our original want line. It was one step removed from it. So we're going to add one extra line here. 8 will give us A, right? Because now we've got not B implies C implies A. And this is just conditional elimination, lines 1 and 7. And now we're done there. Okay, 2 more problems. And these 2 will allow you to use derived rules. And so, although you should have the 10 basic rules completely memorized, I have off in the corner here given you the derived rules that you might want to use to shorten up these proofs. So all of these proofs could be done without the derived rules. You would just wind up inserting a proof of the derived rule in the middle of the longer proof. But that's a pain in the neck. So just bear in mind that for these proofs, you can do things like cancel out negations, right? Not A is equivalent to A. And this goes both directions, as you can see, because it's got the double, the turnstile facing 2 directions. De Morgan's laws comes in 2 forms, and they're both equivalences, right? De Morgan's law says essentially that when you distribute a negation over an and, it becomes an or. And then the other form of it says that if you distribute a negation over an or, it becomes an and. And then we've got modus tollens. That's our one rule that only goes one direction. It's like conditional elimination, only backwards, because it's got the not be. And then the material conditional. All right. So we start out with proving this theorem. P implies Q implies P implies P. This is called Peirce's theorem. It's kind of a nifty little theorem. We don't have any premises this time. We just are starting out with that derivation symbol. So that means that we start out with our Fitch bar. And, nothing above it. And then we need to have a subproof immediately. Okay, well, in this case, the subproof, the thing we're trying to prove is a conditional. So we're going to do a conditional proof. Oh, and this is line 1. So it's for conditional derivation, want P. Alrighty. Well, that gives us something, but not much, because we still need, we just have one premise. It doesn't do anything. So let's do the thing that we were doing in the previous proofs, and insert and run a indirect derivation inside a direct derivation. So what we're going to do is we're going to say not P for indirect proof, and we want a contradiction. Okay. So now look at our premises. There's actually more fancy stuff we could do here. We could try to, for instance, derive P implies Q. I don't know. There's some tricky things we can do. But the easiest thing is actually to go back and notice that we can apply our rule of modus tollens here, right? You have to imagine these are script letters because we don't have a script font in Canvas. But if you know, we know that if A implies B and not B, then A. So that gives us what we were looking for here. We can now say line 3, Oh, and we want to be sure that we're on, keep track of what level we're on. So now we want a contradiction. And we can get not P implies Q, because that is the negation of what was in the line before. Okay. So, this is modus tollens. We annotate it using this abbreviation, and then lines 1 and 2. Now remember, we're looking for a contradiction, right? That was our last want line. So there are two places we could get a contradiction. We could either get a contradiction by deriving P, or we could, then we'd have a contradiction with not P, or we could get a contradiction with not P implies Q. We've already seen that, if we don't want to just go back and try and prove P, we don't have any tools for doing that. But we could show that the opposite of P implies Q. And that's easy enough, and I know we can do it because we're in a contradictory world, right? As soon as I assumed not P, I had created a contradiction in the system. So once we're in this level, once we're 3 levels in here, we know that we can prove anything given enough time and resources because there's a contradiction. So I'm pretty sure we will be able to show P implies Q. So I'm just going to do that as what is now a level 4 subproof. P for conditional derivation, want Q. All right, and you know what? We now have our contradiction written explicitly, right? There's P right there, and there's not P up there. So I can do all sorts of things to get what I want now. I could, for instance, launch a 4th level subproof with, we're actually already on level 4, a 5th level subproof with indirect derivation. But I would rather not have more subproofs than we can possibly deal with. So instead, I'm going to use OR introduction. OR introduction is the other rule that lets us introduce new letters, right? So, watch this. 5, 1, 2, 3, 4. Man, we're in deep. But in any case, I'm just going to say P or Q, and this is OR introduction on 4, right? OR introduction says that you can always, given any sentence, say or and then anything else. In this case, we already know that P is true, and since P is true, I could P or Q. P or anything is going to be true. But we're also in a land of contradiction because we knew not P up here. We've got P and not P, so that means that we can use 1, 2, 3, 4. We can use disjunction elimination and give ourselves Q. So this is the disjunction introduction, disjunction elimination 2-step. We used that in earlier proofs, in earlier problem sets before we even had indirect derivation as a way of getting ourselves new letters. So this is lines 2 and 5. Right? So there's our Q. Now at long last we can start popping out, right? So 1, 2, 3. We have P implies Q. Conditional elimination. I'm sorry, conditional introduction, lines 4 through 6. Okay. Now, why did we want P implies Q? Right? That was our want. That was what we said up here, right? We were doing this conditional derivation. Why were we doing that conditional derivation? Because we could get a contradiction with this on line 3. So line 3 just gets repeated down here. 8. We're at the same level, not P implies Q, and this is R3. So there's our contradiction. That means that we get what we wanted. What did we want again? When we assumed, we got this after we had assumed not P. So we can now write P. And this is conditional elimination. I'm sorry, negation elimination, and lines 2 through 9. And then finally, we can finish out our outermost derivation was a conditional derivation. So we've gone from this all the way to our final want line. And so this is conditional introduction, lines 1 through 9. And we're done. All right. One last problem. We've got not B, and then we've got these premises here. This looks interesting. I wonder how we're going to do that. So, 1. Oops. And then want not be. Well, you can tell right away that we're going to use indirect proof, right? Go here and then so we start with B for indirect derivation, want a contradiction. Well, what can we do? This doesn't seem very promising, does it? Well, fortunately, we've got extra firepower now in our in our arsenal, because we can use these derived rules. So look here, this is a negated disjunction. Because it's a negated disjunction, the rule De Morgan's law applies, right? And the De Morgan's law says that if you go from not A or B, you distribute the negation, it becomes an and then you can negate the two sides individually. So we can do that here. Line 4, we're going to distribute this negation over the disjunction. So we eliminate the parentheses and we add up those. The or turns into an and. So this is De Morgan's law on line 2. Now we've got stuff to work with, right? Because the left side of this conditional, this biconditional here, said if we have A and B, we can get C. So we just need an A. Oh, but look, we've got two negations here. We've got not A, but what we want is A. Fortunately, we've got the rule of double negation. The other thing about the rule of double negation is that it is what we call a rule of replacement. All of these rules that have the turnstiles going in both directions allow you to replace within larger sentences. So we don't even need to pull out A on its own. We can just right now write not C and A and say that's double negation on line 4. Okay. So line 6, we want the we want to put together the A and B, is it? What's up here? Yeah, A and B gives us C. So we say A and B. I'm sorry, first we need the A on its own. So that's and elimination on line 5. And then we can put that together with line 3 to get a B. And note here that we don't need to use a rule of repetition. This is a situation where sometimes people think you might need to use repetition, but you don't, because the B is already in a location where you're allowed to use it. It's not in a subproof that's been closed off. So this is and introduction, lines 3 and 6. So A and B gets us C by biconditional elimination, lines 1 and 7, right? Line 1 is that biconditional. There's our C. And then we get a not C, line 9. Not C is going to be and elimination from line 5. There's our contradiction. So we can end on line 10 with the opposite of what we assumed. We'd assumed B, so we can now get not B, which is what we wanted. Not B, negation, introduction, lines, and the subproof is 3 through 9. And we're done. Yay! Okay, you hit submit, and it's going to say that you have 0 out of 100 points, and that's because these require hand grading. But the correct answer should be visible, so you're good. Maybe the correct answers aren't visible. I will go back and be sure that the correct answers become visible. All right, thank you very much. So remember, there are 5 tests. You can take each test twice. This is the last test of the section, and the tests are 60% of your grade. The homework is 40%. So you don't need to get all A's on the tests to pass the class, but you do need to be sure you turn in all your homework to boost that up.